Welcome back, everybody. Um, I want to thank the organizers, Mushin and John, for organizing specifically this panel, for having with us Hanno, Jurek, Lorraine, and Francesca. I've been asked to chair this panel to moderately and vigorously. So the rules are gonna be, each one of our, we are gonna start with a 4-minute statement from each one of our panelists. It's gonna be timed, 4 minutes, no interruptions, no slides. I know the rules are arbitrary, they are completely arbitrarily made up. Sometimes creativity comes from arbitrary rules. Think about poetry, think about football, think about constrained Hilbert space. That's what we are gonna try, okay? Who's gonna start? Hanno, would you like to start? Please.
Okay, thank you very much, Eugenio. So I have seen many beautiful new developments in this conference. There was the computable spin-foam models and the numerical evaluations where you can now sum over, like use multiple vertices, not just one. So that's very nice. I have heard about the fate of black holes, where there are much more concrete scenarios now that are under investigation, so very fascinating stuff. Quantum cosmology and other symmetry-reduced models like black holes, that's now a precision science. I'm very, very impressed, and support comes from group field theory, from the methods of loop quantum cosmology proper, and also from path integral spin-foam methods, so very solid foundations, very, very, very nice. Boundaries, lots of new interesting things, both in the quantum theory and in the classical theory, so that is all very, very nice. Let me also say that there were a couple of things where it's not like I didn't see them, but they were more like in the parallel sessions and so on. So we could have more of that, in my opinion. On the one hand, foundations. Yeah, so the connections between these core areas that we have, the connections between canonical and covariant loop quantum gravity, canonical and spin foams. Yeah. Also the connection between loop quantum cosmology and the full theory. It's not like we don't know things about this. There's been a lot of work, and we understand this fairly well, but I think it is important to work on this more. Also, numerics in canonical loop quantum gravity, there are now things starting up, but I think we have way to catch up with the spin foam people. Planck scale degrees of freedom. So Alejandro emphasized this yesterday in the panel, and I want to jump in the same, into the same battle. We are missing something when we do these symmetry reductions, and that is the local behavior of our states, the local degrees of freedom. And they are exciting because there can be entanglement. Yeah, so a spin foam is a quantum computation on, if you look at it in the right way. So there could be a quantum information viewpoint brought to this, and ultimately there could be physical effects that are coming out of this. So I like local degrees of freedom. I want to understand them more and dynamically. And my final point is not a physics one, but I saw a lot of grace and kindness in how the participants interacted with each other. So great compliment to all of you. But this is also a thing one can never have enough of, because science is super hard, and we are human, and we need encouragement and of course also criticism and advice and so on and so forth. So let's all walk in each other's gardens of ideas very respectfully and happily. And yeah, that I think ends my remarks. Thank you.
Thank you. Jurek.
So what I like about our field, and we could see it also in this conference, that for the first time after long time, we really come up with some predictions that can win Nobel Prize. So we already have this prediction that black holes turn into white holes. So if in one day astronomers see white hole, then Carlo will knock the door and Abai, and they will say, hello, we already predicted this. Well, we now have this specialized version that those black holes actually are very small and that they're micro black holes. And I don't know whether astronomers are right people to look for them, but if somebody finds this small micro white hole, then then it is also something which is conceivable. And also related to this subject of quantum effects and black holes is this result of Yongge Ma and Zhong Zhang and their collaborators, that they predict that there is a possibility that through this either black hole or white hole, we can see some other black hole that was before this process, and that then it will change the image. So the structure of those rings will be affected by this quantum matter. I'm not saying that I guarantee that it's going to happen, that we are going to see those white holes which Carlo and Abai predict, or those rings, but at least this is somebody bought coupon. If there is lottery you want to win, you have to buy coupon, and otherwise you are not going to win. Then this is for sure. So I'm very happy that there are such strong hypotheses can be formulated. Other than that, I like very much that there is again interest in going back to the Ashtekar complex or self-dual Ashtekar variables and foundations of loop quantum gravity. This is something which we didn't finish. We just were happy that we can do with SU2 connections. So we reformulated theory such that SL2 connections turn into SU2 connections. But it would be much nicer if we were able to do it in original connections. So I was it was very interesting to see different approaches. Probably the most the most systematic work was this by Hanno. I'm sorry that but I just coming back from your lecture, so in which this subject is really systematically studied. And I also mentioning this because it was a parallel session, and we not all of us participate in all the parallel sessions. There was also talking about isolated horizons. There was also this very nice result that all the idea of isolated horizons, which comes from Abai, is that let us describe black hole from within. That we don't need all space-time that contains black hole, but let us describe black hole from within. Should I stop, or I still have 10 seconds? And now we know that we can even prove such theorems like rigidity, like the fact that black hole has a unique, in the extremal case, black hole has a unique shape, and that this shape is given by local law rather than by some global considerations. Thank you. Thank you.
Laurent.
Okay, so first I want to start with maybe a non-scientific remark. I want to celebrate the fact that we have a constitution, which has been voted, and we are going to elect a new board that's going to help, make that community thrive and go to the 2.0 version and the future. So I'm looking forward to that. I think it's a great step for all of us.
Thank you.
No, everyone that was part of it. I'm looking forward to that. So now I want to go back to what you were saying. I want to go back to why is there an LQG community, to the foundations of the field. And then, I can give you my perspective. For me, it's really that, I want to understand, and this is what the original part, we really want to understand what is the nature of UV divergences in quantum field theory and how quantum gravity and quantum geometry can resolve it. In the modern language, the proper way to say that is that we want to understand what is the nature of quantum entanglement across subregions which are mitigated by gravitational. This is the proper way to ask the question there. Now, why do we need that? In QFT, even what I'm going to say is even in renormalized, fully renormalized QFT. You know, when you cut QFT in two halves and you look at entanglement, you can define what's called the modular Hamiltonian. That is the operator you get by tracing out half of it, and that proves that the other half is a thermal state, and there's an Hamiltonian there. It's called the modular Hamiltonian. The expectation value of that modular Hamiltonian is the entropy. What's the value of the entropy in QFT? Infinite. But and then it's even better than that. What is the value of the fluctuations of the modular Hamiltonian, which is the fluctuations of energy along null rays? Infinite. What's the fluctuation of the cubic? Infinite. So this is the one, and even if you completely renormalize the theory, so quantum gravity is not a fully renormalized theory. Some people have said that. It's not because even renormalizing the theory will not put this infinity to finite. You need quantum gravity for that. Okay. So that's the baseline. So, you know, quantum gravity needs to regulate UV divergences. How does it work? So let's you know, the first part is like the success story of LQG. So the discovery of LQG, and it was the first one, you know, to do that. Now there's many more people that focus on that, was to say, well, okay, entanglement across subregion is due to gauge invariance. And the gauge invariance at play is SU2 gauge invariance. And then if we quantize, we cut open that object, we get this SU2 charge, these are the flux operator, boom, they have the discrete spectra, we regulate the operator. So these two results, they will stay forever. Like entanglement is connected to gauge invariance, and the operator, the area is an operator, okay? So we all feel warm and fuzzy about LQG, okay? But, you know, I was asked to say something controversial, or at least provocative. But now, so this is all good and great about LQG. But the problem is that if I follow the same reasoning, it's also along the same way very clear that LQG is not a theory of quantum gravity. That is, it's not a framework that is complete, and it needs to be completed. And here I'm not talking about I'm not talking to the old generation, I'm talking to the younger generation. So don't believe the old generation that says that LQG is complete. It is not, and let me give you the reason. The reason is exactly for the same reason. The reason is that SU2 is one of the gauge invariants, but that's not the only gauge invariance in the theory. In fact, it's not the most important of the gauge symmetry. Diffeomorphism symmetry is important. Local boost transformation is important. And the main thing that we have understood very cleanly, very sharply in the corner symmetry approach is that anytime you have a gauge symmetry, there is a new form of entanglement across subregion. This is unavoidable. Now, one of the hypotheses of LQG is that diffeomorphism invariance doesn't create new form of entanglement. So that's why it cannot be a description of quantum gravity. Quantum gravity is a theory where diffeomorphism gauge invariance creates new form of entanglement. And that's where we need the next generation. And, okay. Am I done there? Good.
Thank you, Laurent. I appreciate that.
Is it working?
Francesca.
Yeah, I am the younger on this stage, but I'm gonna play the old person, the old lady. I remember many, many years ago when I started working in this field at my first conference, that there was this mantra saying, oh, the theory is not complete, is not enough defined mathematically, so why are you trying to make predictions? Because first we have to understand all the subtleties, all the things, for instance, concerning the different regularization of the Hamiltonian and so on, and then we will make predictions. And I always reacted to this, and I think we are still here saying we have really to make an effort in these communities to try to make more and more prediction and try to connect more and more with the communities who make observations, and observations both in cosmology, in gravity. We have an amazing field that is brand new, that is gravitational waves. So we really have to be attentive of what is happening there. Attentive, for instance, with with the James Webb Telescope. We have to be attentive of all the new discoveries that are happening there, and we have to be attentive to all the discoveries or the improvements that are happening, for instance, in the field of quantum computing and quantum information, because, I mean, we have also an opportunity for an experimental setup there, for instance, with the simulations on a quantum computer, that could be very relevant for us. But of course, say that there is an interplay between theory, observations, phenomenology, and numerics. So it's not that you advance in one without the other. Very often is a back and forward between these different things. So indeed, we need people who work on one and people who work on the other. And there is a continuous backfeed between these different things. I think, for instance, to what happened in the numerics. And by the way, I think that the advances in the numerics have been spectacular. So a few years ago, again, when I was young and I started, of course, other fields of other approaches to quantum gravity were much more advanced than us in doing numerics. But nowadays, I think we are really doing well in that respect. In a certain sense, the numerics are even surpassing the things that we know about the theory. So we see things that are beyond what we understand analytically. But this has already happened in the past because, again, I'm playing the old person. I remember when people were developing the APRL vertex. They were the first numerics done by people like Magliaro and Perini with Speziale and so on. And the first numerics were giving us indications of the right direction in which we had to develop further the spin form construction. So it was always a feedback between advancing in the numerics and then advancing in the analytical construction of the theory and then doing another advancement in the numerics and then advancing again. And then, of course, also being constrained by phenomenology. So, for instance, we had a fantastic advancement with Lorentz violation that has not been seen. So, in a certain sense, even if in our community some people were working on this, but somehow this reinforced the idea that the theory with which we work is a theory that is a version of a gauge theory that is based on the Lorentz group, on the Lorentz symmetry. So I think we will talk more about all these things, but maybe I should stop here and just keep in mind. So sorry, just the advice for the young people is don't stop yourself from working in the numerics. It's not just a boring work about doing coding. It's actually learning more and more about the theory, and the same when you do phenomenology, you learn about the theory, you know about the numerics and so on. And just one last thing that is maybe a bad note. We had a leaky pipe in our community. That is the fact that we lost the numerical guys. So we need more of them. And that's up here.
I have a formal request. Let us, since now, let us stop clapping after each statement. Because it's just too much.
You are now free. So this was fantastic. I have so many questions, but I'm not going to ask them because I would like you to comment on statements that you made. Short questions with short feedback. Who wants to start?
I can shortly comment about this. What you said, that loop quantum gravity is not everything what we can do because of we have a CO2 gauge transformation, but there is Lorentz boost. So this is exactly why I second this effort to formulate self-dual theory in terms of the self-dual variables, because they have full SL2C including the boost. So we agree that this is worth doing.
And in this context, Laurent actually has a very nice paper out that you should also read. It's very, very nice.
I was mentioning also diffeomorphism. That is, in LQG, we represent diffeomorphism acting classically on the link. But when you look at for instance, the corner, there exists. You can classify the representations of diffeomorphism, and you have other representations which creates entanglement. So I think that's also the next step, which is related to boost in space-time.
More comments? Go ahead, Laurent.
I'm not sure if it's a comment, but maybe a question for all of us is, I would like to hear each one of the participants, what do they think is the experiment or the way where we're going to discover quantum gravity or prove LQG wrong or right?
Good. It's a question I'm going to have for the four of you that we got from the audience. Are there more comments on the statements we just heard?
I mean, I like that many of you talked about these big effects of loop quantum gravity. I remember 2 loops ago, Lee saying this, guys, also look out for the 0th order effects of loop quantum gravity, not just sort of for the epsilon here or there, but the 0th order effect. It's great. I mean, of course, these are nuggets of gold. Yeah, we don't find them often, but we should also think about them.
There is one thing which was mentioned by Francesca and others, which I hesitate. So it's not that I want to express some criticism, because part of me supports this, but part of me is a little critical. So this concerns observations and applications in other fields. So we have this, physicists have this tendency of building some theoretical reality from completely different models, which are completely not compatible with each other. So when there were those clever guys who happened to know quantum theory and relativity, and then they came up with the idea of Hawking radiation. And okay, so we have Hawking radiation, fantastic piece of art and science. But now we consider Hawking radiation as some absolutely confirmed reality, and now we want to see it in our loop quantum gravity. I'm not 100% sure that we should go in this direction. Maybe usually when new theory is formulated, then some new things happen rather than just new interpretations for something which already had been earlier introduced. But on the other hand, it's fun to learn that our young collaborators working on loop quantum gravity can also learn very well other sections of quantum field theory and apply it somehow, combine loop quantum gravity with them. So there is a social advantage of and educational advantage of this.
Can I react to this? Thank you, Jurek. So what I was trying to mention before is to be attentive to what happens in experimental physics, or observational physics. A different story, and of course we wanted to learn from other community and so on, but at the same time we should not fall for the new fashion. I think that in this community there is some knowledge, and in a certain sense the other communities are rediscovering this knowledge that was already present in this community back then. So maybe what we have to do is rather to capitalize on this knowledge, and we have maybe something to say with these other communities.
Yeah, if I may extend on that, that was part of the remark I'm saying. I'm saying that, 20 years ago, loop gravity was the first one to say that entanglement and gauge symmetry are connected. Somehow, there's a focus on different, more numerical, more phenomenological, that let go. What's happening right now is that people are rediscovering that, and they're forgetting it's coming. So it's coming from this community, and maybe in some sense they're kind of passing us by. So I think for me it's a little bit of a wake-up call. Like, you want to connect. It's great that there's other people rediscovering similar ideas from different perspectives. But if that community wants to not become irrelevant, it has to rediscover this idea and be working actively on it, not just letting it dormant for the past, as we have been doing for the past 18 years. I think it's important that we go back to the theoretical foundation of the field too, because other communities are understanding that, whether it's because they're thinking about the infrared, it's because they're thinking about quantum experiment in interferometry, it's because they're thinking about the quantum foundations. And then I see more and more papers appearing where they're discovering ideas with zero credit to this community. So I think I would encourage you to be first connect, as Francesca is saying, but also be more proactive of saying, look, this is, maybe write these old ideas in the new forms and make the connections with what's happening. Because, anyway, I worry that otherwise we become forgotten.
Well, there is only a problem that if you want to name something, you have to be the second to say it. So,
yeah, okay, but yeah. Anyway.
Good. Shall we move to the second part? So I received plenty of questions that I tried to summarize. Definitely in an unfair way, I blocked them into groups. I blocked them into three main groups: foundations, global sociological aspects, and phenomenology. So I would like to go through these three, dividing more or less the time that we are left, by first, not reading, but summarizing some of the questions, and then letting people from the audience ask more for each one of these three topics. And let's try to, make sure that we cover all three of them. So I would like to start with foundations. Anybody can jump in, don't wait for me to. So we got lots of questions. One question that jumped up about foundations is, what's the role and status of causality in quantum gravity?
So can I start? So this is a great question, and I think that this is something which we should think about when we want to contribute to understand quantum black holes. So we have various approaches to quantum gravity, either canonical or spin forms or some symmetry reduced models. But in that case, we would need to really reconstruct space-time from our states and operators, and then try to see in what way we can define causality in way knowing what it is in classical theory. So I think that this is some area which is thus far a little abandoned, and that we could develop this, and in particular we could also understand scry properly, whether scry is just classical property or if scry is also property which exists in quantum theory. So this is, I think this is a very, so the answer to the question is that there is a lot to understand, and it seems that this is not an obstacle, that this is a very interesting problem to work.
No, I want to say, I think it's very, very, very important to understand causality. Now, what do I mean by that? Is that part of causality is null nines. The thing that distinguishes, Lorentzian spacetime from Euclidean spacetime is the existence of null cones. And, we had two talks, like Souvrat talks about that, and Wolfgang talk about that. And I think, it's kind of amazing that we're just starting to understand what is the nature of quantum null rays. And we could have done that 50 years ago. It kind of bugs me that we were trying to quantize Wheeler-DeWitt equation, and that's not the right thing to do. So, of course, understanding the quantization of null rays is absolutely foundation, and it's one of the key elements to understanding causality. I don't know why we waited so long for doing that, but again, for the young generation, this is amazing. It's like, it's happening now.
Actually, just to clarify that when I arrived in Syracuse 30 years ago, already then people were working on null surfaces and quantizing. So this is not new subject, but perhaps now we will bring something really new.
There's been a lot of
make
very recent new results on it.
Yeah, it's a very good question. I think it's difficult. It's just a difficult question how to get one's hands on it. Maybe we have to think about correlations more, like how spatial correlations are different than time-like correlations and so on. Great question, but just how to answer it, how to do it is difficult. But that's why it's good to have many young people. They can have good ideas.
So I want to follow up on what Hanno was saying, that of course, when you talk about causality, you can mean different things. So it's important to clarify at the conceptual level which particular notion of causality you're talking about. So, of course, people have been trying to insert causality in our spin-form models, even at the time when we had still Barre-Crane with Oriti and Levin, and then Eugenio, of course, with Pierre, was working on this. Even Giorgi Mirzi, the good old Giorgi Mirzi, had a paper on this and so on. But let me also, so this was within our community, but let me connect with something that is happening in another community, that is the one of quantum information, in which people are talking about quantum reference frames. And they are somehow discovering the fact that there could be a superposition of causal structures. And this is exactly what quantum gravity is about. So in fact, more than finding a defined causal structure, that is what you have in the classical theory. What you want is to understand, to digest what happens when you have superposition of metrics, and namely superposition of causal structure. That is quantum gravity.
Thank you all four of you. I have one more question, and then I'm going to give the mic to the audience. There's another question that's come up that is matter in quantum gravity. What are prospects? What's the status? Not just look quantum gravity, your overall perspective on the role of matter in quantum gravity. Who wants to go first? Hanno, go.
Well, I mean, let me answer from the perspective of canonical branch. So on the one hand, there is this, this procedure that we follow, and then a lot of matter can in principle be coupled. But there's nothing obviously beautiful happening. On the other hand, if you look at the basics, that sort of a fermion is just an open end of a spin network, and then I think maybe there could be some sort of unification happening, and perhaps this is something we have to think about more. That from our simple principles, maybe matter can be not just quantized from some classical theory, but maybe matter can be put in a more elegant way. And certainly I'm not the first to say this. Many people have even had concrete proposals for that.
Yeah, so maybe if I try to make it systematic. So actually, Hanno pointed out that some kind of matter may even emerge from loop quantum gravity rather than be put there by force. And on the other hand, we have two approaches to matter. So one approach is that we treat matter in the similar way as the other as gravity, which means if this is Young-Mills field or Maxwell field, then we put it on. Then we also add some numbers to our spin networks, and then those numbers characterize holonomies of this Young-Mills connection. If this is scalar field, then we tend to put it on vertices and also do some more or less awkward procedure of some pre-discretization, and then later we believe that it in fact gives a continuum theory. On the other hand, there is this approach of swallowing matter, which was introduced first by Karel Kuchar, and later I think that Christina is here the biggest expert in the audience on how we can swallow up to 4 scalar fields. And then when matter is swallowed, then it actually is not quantized, because then it uses as time or some, it can be used as some coordinates that are not quantized, that are used, that are not physical degrees of freedom, but in this way we eliminate those gauge degrees of freedom. So this is a second way of approaching matter.
Sure. Okay, just a comment on this. Yeah, there was the question online was about somehow having matter emerging from quantum gravity, and I am less interested in this because I don't think that quantum gravity will solve all the problems of physics. And I like loop quantum gravity because we can just couple the standard model to it in a way that works. On the other hand, now, while I was listening, it came to my mind, yes, there is a kind of matter that emerges from quantum gravity, possibly, this is my hope for the Nobel Prize, and this is dark matter.
Yes, those small...
Yeah, so maybe there could be remnants, or there could be particles at the Planck scale with the Planck mass that are out there, and they are predictions of quantum gravity, and they may be dark matter.
Okay, so is it working? Yeah. I guess I have to be the bad guy now.
Your turn.
Yes, okay. Okay. I think, I know, and I want to be fair to the field, but I think it's fair to say that, loop quantum gravity is defined, and the beauty of it is really it's designed as a theory of geometry and focus, and its strength is really to think about, what is pure gravity and pure geometry, and that matter is an afterthought, it's the parent pauvre, and it's arising in a very clunky manner. So let's examine some of the proposal which is there, because in fact it goes back to the point I was making. Okay, you have a spin network and you put a defect there. And by the way, this idea works exactly perfectly in 3D, but it doesn't work with LQG. Why it works in 3D? Why it doesn't work in LQG? Because in 3D, the spin networks that you have, they carry momenta. So it goes back to what I was saying, is that in 3D quantum gravity, the states that we can construct, they know not only about the Lorentz transformation, but they know also about the diffeomorphism and the translation. And of course, if you now put a defect, matter, usual matter, okay, maybe carries momenta. That's the point. So if you want to have matter, you need to have a quantum number in your quantum gravitational state that you can assign to momenta. There was a very nice talk by Simon this week where he was proposing, and also it's kind of similar to maybe what was discussed this morning about the fact that we need to go to the second stage. The second stage, the first stage is we only have Lorentz invariance and we only have the B field. The second stage is that way we need to have the frame field and we need to have translation. And before we have a notion of what is the momenta operator, and before we understand the level of entanglement due to the momenta operator, we do not have matter.
Good. We have to do
Just a little,
Please.
just a little. I mean, you might be right. I find this very beautiful, this idea of making the gauge group bigger and going to these extended spin networks, yeah? But we can write down a momentum density for fermions or something like this, right? And they work, this is an operator, presumably, that works on the spin networks and on these defects. Yeah? But maybe it's not beautiful, and I would be open to proposals where the particles come in more naturally, 100%. But that we don't at all have momentum, I have to disagree.
Yeah, maybe I'm speaking at a, let's say, more fundamental level. I go back to the project that, can I think of LQG or LQG 2.0 as some kind of fundamental description of geometry? And geometry allows translation, that's what I'm saying. So whatever is the quantum notion of geometry that we don't have yet, there has to be at the fundamental level. Now, if you want to do an approximation, a simulation, and a large quantity, for sure, you can take any lattice and couple and write some approximation. But I don't think that's, okay, the project I'm talking about is the beautiful project of self-duality, like this kind of pure, maybe there's a way to access some element of the foundations of quantum geometry. And then these elements, we repeat, if for that project, needs to carry the elements of momenta. I mean, it's in the same way that it's not enough to just have the B field, you need to have access to the frame field. It's as simple as that.
I have a suggestion. The next loops is going to require a panel on matter only. We have 2 years to prepare.
Yeah. But maybe I would like to summarize.
Yes, and think carefully about one question. I'm going to select one question. I want to see hands, and it's going to be unfair.
The bottom line is that matter cannot be coupled to loop quantum gravity, quantum matter, in the way it is defined in the standard model. So we have to completely reformulate the theory of matter and interactions to make it compatible with loop quantum gravity.
One question, Surat, on foundations.
It seems to me that one of the things we have learned about gravity in a different context, I know which some people maybe in the community don't like to think about, but if you think of gravity in asymptotic ADS, which is the legitimate theory, it's a toy model of gravity, we have learned that it's holographic, and in specific examples, we have very precise examples of that duality. And it seems to me that there should be, I'm wondering if there's some, if there's some hope of trying to understand how from an LQG perspective we get a holographic duality, because I think that could help to clarify many things, also make links with the completely different community. Whether if you define LQG in ADS, do you get a specific conformal field theory, and what are the properties of that conformal field theory? And I think these are interesting questions which one could try and ask. Or maybe if there's a contradiction, if you don't get a CFT, that would also be interesting.
Yeah, I can. I mean, so let me go, let's say, halfway towards you. Like, on one hand, I feel like in the past 35 years, I've learned 2 things about quantum gravity that will not go away. The first thing is that, the area is an operator and it needs to be quantized. I will not let go. Like, that's one thing. On the other hand, I kind of agree with you, but I will have to define my term, that gravity is holographic. There's no other way to say it. Like, I don't even know, yesterday the question, can it be holographic or not? It absolutely is, in the very simple sense, because the existence of the constraints, if you give me, and you ask me, what is the energy of a finite region? It's in the corner, it's in the boundary term, entirely. There's no other theory that does that. That's what I call local holography. And that property is the property we need to build on. It's the same thing I was talking about, the property of entanglement that connects the nature of fluctuations. So the area is quantized and gravity is holographic. I think it should be in 2024, we should be the baseline on which we are. Now, by holography, do I mean the global ADS holography? Maybe not. There's maybe holography 1, 2, 3 different level, and some definition might not, survive, but I think it's, if we put these 2 ideas together and we start from scratch, we can go a long way.
Good, thank you. I would like to move to a separate topic. So we got lots of questions that are of a more global, sociological or relation kind. And I selected one, just one. And I rephrased it in this way. The last time you spoke at a non-loops conference, what argument from loop quantum gravity sparked the most curiosity in the audience from another field? What worked? What sparked the most curiosity? What worked? In a talk to somebody from another field. Francesca.
Not the most controversy.
Well, let me say that it depends on which conference are you talking about. If you are talking about the philosophy of physics conferences, of course, people are very happy because we have kind of a complete theory on which philosophers can carry on discussions about the ontology of the theory and so on, or about the nature of singularities as we have singularity resolutions and so on and so forth. Then when you go to astrophysics conferences, they are of course very curious about possible phenomenology. For instance, if black hole explodes, back then they were exploding, now we have remnants, so they are very curious about this. There are ideas about remnants that are independent but not motivated, so we can bring a motivation. So this is another thing. Then you go, for instance, to mathematics conferences, and by the way, in a field of mathematics that is non-commutative geometry, this is a way to recover the standard model, except that you need an ingredient to do that. You need an underlying non-commutative space-time, and oh, by the way, in loop quantum gravity we have it, so they are very interested, and I can go on, I think. But the point is that it's not just one community. We have plenty of communities that are interested to hear what we are doing. And by the way, also, the last time I went to an art meeting, they were very interested because what we think about space-time in a novel way, even artists are very interested to hear about.
Thank you, Francesca.
So I think Francesca answered the one part of the question. Maybe I'm going to take, for me, the question on what triggered the most controversy, but in a way that is so surprising to me that this is why we need this community, okay? So I often, I'm at Perimeter and I'm in contact with a lot of particle physicists, ADS, CFT. So something which is very controversial in the rest of physics is a simple statement like, geometry is quantum, and that will help resolve the UV singularities. You say statements like that, good luck. And it's and that's why we need a community that for which it's kind of natural. And of course it's natural. So the day maybe this statement like that will not become controversial ever, I think we'll have only one big physics community. So it's still a surprise to me that it's such a it trickles people in so much deep way.
So I also encountered exactly the same. So some, depending on who you talk to, so if you talk to physicists, then they ask, so what about renormalization? And then we say we don't need to renormalize. Although now I learned that actually people are looking for renormalization of loop quantum gravity. So this is one of other examples when we want to bring some frameworks, other frameworks which maybe are not necessary in our case. Or if you talk to people doing more mathematical approaches to quantum field theory, they ask us, so you guys can multiply two operators and you don't have to regularize this product, or yes. But on the other hand, somebody noticed, I think Herman Nicolai, that actually the fact that in our case everything is finite, it doesn't solve the problem because we have ambiguities, and this is the same what renormalization, what non-renormalizable theories have. And one more thing which I also very often see that other people find controversial is background independence. So physicists are used to background independence, and they sometimes think that if as long as we are background independent, we are not going to to achieve any physical result.
One hand up from the audience. I have plenty. Yes. Samar.
What do you think people in other communities, like the string community or other quantum gravity communities, do really well that we don't at all?
Networking?
Well, I think that that our framework is particularly incompatible with other frameworks. So this is one of the problems that social problem. In other areas, if you learn and believe in perturbative quantum field theory, then if you see some other theory which relies on perturbative methods, then you can change or extend your area of research. But in our case, if somebody is doing high energy physics and wants to join us, then there is no way of continuous transition. So the fact that we are little, but due to those applications which we try to do, maybe we get closer and we build some bridges with other communities.
Good.
I mean, I really like that question because I think, you know, different perspective have maybe different anchor points and make certain things much more efficiently, you know, available. And I think what's happening right now is more, I think the next phase is more about creating bridges. So let's say maybe keep what is really valuable in LQG and shed maybe the extra unnecessary clunky bits, and do the same thing on the other, you know, cross of the aisle. And we have, I think there's new breeds of physicists. I mean, Suvrad is an example of someone who is starting from, you know, I mean, I pick on you, but, you know, string theory, but then, you know, picking elements of asymptotic infinity, quantization, quantum gravity, and then personally I feel I'm doing that. And I see more and more people which are just exactly trying to do what is the most, you know, efficient way, what do I keep in that approach, and what do I keep in, you know, in mind, and then create the bridges. This is for me the future where we should go.
Good, new topic, phenomenology. And we are constrained on time, so I'm gonna choose this question that as an undergrad in a particle phenomenology group, this was the way they were phrasing the game. The game is, place your bet. What is the first observation of quantum gravity effect going to be? Put also a deadline. A deadline. When is that going to happen?
The VLAN effect that has already been seen. The bound on luminosity for gravitational waves.
The VLAN effect. I like that. Okay, we have a name now.
The VLAN effect that we heard about this morning. Okay, but beside the jokes, and by the way, the result by Wolfgang is really something we should try to exploit, understand better. But my point is that I believe that we have already seen quantum gravity. It's just that we have to recognize it. So that's why I was saying, let's go and look for results for current data, because so another possibility is with dark matter, maybe it's primordial black holes, and primordial black holes may be supported by quantum gravity, not just in the form of remnants, but also because the excited states in the early universe from loop quantum cosmology can produce a different ratio of primordial black holes of different masses. So the point is that I believe that we have already seen quantum gravity. It's just a matter of sharp our eyes, understand where this opportunity is there for us.
Okay, so maybe 3 points. First, I agree totally like with Francesca about the fact that, you know, with insight in every paradigm, we know that water boils because it's made of molecules. The sky is blue because, so, you know, the evidence for quantum mechanics had been observed for 10,000 of years. It's just that, you know, we only realized after. So it's you know, I think it's maybe we're looking at it with the wrong eyes, and it's really thinking about, and I think in the next generations of Loop Conference, I would love to see more phenomenological approach in the sense, you know, how do we think about new observables? So that's the point. Now, if I go maybe more loop quantum gravity, and then I'm going to answer your question. Okay, there is clearly loop quantum gravity stems there's on one thing, which is the area spectra is discrete because there's an Emir-Z parameter. The Emir-Z parameter is a low energy parameter. We need to observe it, and I wish there would be, you know, sessions on that. So can we observe it classically? And then, okay, there's proposals there, and we can talk about it. But I think we need to seriously, you know, rule it out or find ways to measure it. Now, on my bet for quantum fluctuation, I think I go back to you know, how we discover the molecularity of matter, quantum mechanics, Brownian motion. Why was it Brownian motion? Because we use infrared UV mixing to beat the odds. So if there's no UV infrared mixing, if there's no observable that has UV infrared mixing, we will never, ever, ever discover quantum gravity. Okay? And then if you believe in effective theory, then you should leave the room and stop doing quantum gravity and do something more useful. So we should be thinking about what is this observable? What is the Brownian motion effect? It's about what I was talking about. It's about the fact that there are fluctuations. What is the prediction of fluctuation of geometry in quantum field theory? Infinity. Well, infinity is a pretty big number. So and in fact, there is experiment designed right now to measure this quantum fluctuation of geometry. The timeline is less than 10 years. It's a long shot, but there will be a definite result.
Good, thank you. We have a time constraint, hard time constraint, but I want to give you the opportunity to place your bet. Place your bet.
I don't know. I mean, I'm very torn because on the one hand, what Francesca says is, and Laurent also is very right, that maybe it's staring us in the eye and we don't see it. On the other hand, we get incredible data from, outside of our Earth, from the universe, and so super high energies and so on. And so I could also see something coming from there. I don't know, but I think we are close. I don't know. I hope in the next 10, 20 years we will hear and see something.
Thank you, Anne.
So I already mentioned those two predictions, although I didn't say that they are very probable and that to be true, or that it's easy to observe them. So, and your question also gives some measure of time. But I think that more down to earth and realistically, we should expect some measurement which proves that gravity is not classical. And this, I think, probably this measurement will not show that loop quantum gravity is correct or string theory, but that will prove that there that quantum states which are in space-time, that they also have some phase coming from quantum gravity.
Francesca, 30 seconds and we close.
Yeah, so two things. One is that, of course, among the observations that we have, there are those of the CMB, and there are anomalies there. People like Ivan Agul have been working a lot to connect these anomalies with loop quantum cosmology. This is one thing. And the second thing is connecting with what Jurek was saying, the fact that in the community of quantum information, and thanks to this bridge between quantum information and loop quantum gravity, people are now developing these experiments for superposition of space-time. And our guy, Carlo is involved, and Mario Christodoulou is involved, and all people in Vienna and experimentalists like Markus Aspelmayer and Sugato Bose are involved in creating those experiments. And as Jurek said, this is not a confirmation of one particular approach to quantum gravity, but if we prove that gravity is quantized, this will put us in an amazing position.
Thank you. I'm really happy. This was good. Thank you.